Preparing for a MLOps Engineer interview? You've reached Candy Mentor, and this video is for you. We'll walk through 25 key questions you're likely to face. For each question, you'll see a sample answer followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. What is MLOps, and how is it different from traditional DevOps? MLOps is DevOps adapted for machine learning systems. I still care about automation, testing, deployment, and reliability, but ML adds changing data, probabilistic behavior, feature pipelines, experiments, and model drift. In DevOps, the artifact is usually code. In MLOps, artifacts include data versions, features, trained models, metrics, and environments. A strong MLOps process makes model development reproducible, deployable, monitored, and safe to retrain over time. While answering, focus on the ML lifecycle, data and model dependencies, reproducibility, monitoring beyond uptime, experiment tracking, retraining, and how CI/CD expands into continuous training. Question 2. How would you design an end-to-end machine learning pipeline for production? I would break the pipeline into independent version stages: data ingestion, validation, pre-processing, feature generation, training, evaluation, registration, deployment, and monitoring. Each stage should produce artifacts with metadata, so failures are traceable. I would orchestrate it with Airflow, Kubeflow, Prefect, or similar, and store models in a registry. Before deployment, the pipeline should enforce quality gates like accuracy, bias checks, latency, and schema validation. Make sure to cover ingestion, validation, pre-processing, feature engineering, training, evaluation, registry, deployment, monitoring, retraining triggers, orchestration, and clear artifact version management. Question 3. What is the purpose of a feature store in an ML platform? A feature store centralizes how features are created, stored, discovered, and served. The big value is consistency. The same feature definitions should be used during training and inference. I typically separate offline storage for training from online storage for low latency serving. A good feature store also supports point-in-time joins, lineage, access control, and monitoring. Without it, teams often duplicate transformations and accidentally introduce training-serving skew. In your answer, talk about feature reuse, offline and online consistency, point-in-time correctness, feature ownership, low-latency serving, governance, and avoiding duplicated feature engineering logic. Question 4. How do you handle data versioning in MLOps? I treat data as a first-class artifact, not just an input file. For versioning, I use immutable dataset snapshots, partition tables, object storage paths, or tools like DVC, LakeFS, Delta Lake, or Iceberg. Every training run should record the exact data version, schema, pre-processing code, and parameters used. That lets me reproduce a model, audit decisions, compare experiments fairly, and roll back if a bad dataset contaminates production. Be sure to mention immutable datasets, metadata, schema versions, lineage, tools like DVC or Lakehouse tables, reproducibility, auditability, and connecting data versions to model versions. Question 5. What is a model registry, and what metadata should it store? A model registry is the source of truth for trained model artifacts and their lifecycle. I expect it to store model versions, evaluation metrics, training data references, framework versions, hyperparameters, signatures, owners, approval status, and deployment history. It should support stages like candidate, staging, production, and archived. The registry gives engineering, data science, and compliance teams a shared workflow for promotion, rollback, comparison, and governance. While answering, cover model lifecycle stages, versioning, metrics, artifacts, ownership, approval status, deployment history, dependencies, training data references, and rollback support. Question 6. How do you make ML experiments reproducible? Reproducibility starts by capturing everything that affects a run. I log the code commit, data version, configuration, hyperparameters, random seeds, package versions, container image, hardware, metrics, and artifacts. I also avoid hidden manual steps by running experiments through scripts or pipelines. Some operations are not perfectly deterministic on GPUs, so I document that limitation. The goal is not magic perfection. It is making results explainable and rerunnable. Make sure to cover random seeds, deterministic environments, dependency pinning, data snapshots, code commits, configuration management, hardware differences, experiment tracking, and artifact logging. Question 7. What are the common model serving patterns in production? The main serving patterns are real-time online inference, batch scoring, streaming inference, and embedded or edge inference. Real-time APIs fit user-facing decisions where latency matters. Batch scoring works for scheduled predictions like churn lists or risk refreshes. Streaming inference handles event-driven use cases such as fraud detection. I choose based on latency, throughput, freshness, cost, and failure tolerance. Model servers like Kserve, Seldon, or BentoML help standardize deployment. In your answer, compare real-time APIs, batch scoring, streaming inference, embedded models, serverless deployment, model servers, latency constraints, cost, and operational complexity. Question 8. How would you decide between batch inference and real-time inference? I start with the business requirement, not the technology. If predictions can be pre-computed and consumed later, batch inference is cheaper and simpler. If the decision depends on live context, like current cart behavior or fraud signals, real-time inference is necessary. I also consider model latency, traffic spikes, freshness needs, and failure impact. A hybrid approach is common. Pre-compute stable features or scores, then use real-time inference for the final decision. Be sure to discuss latency requirements, prediction freshness, traffic patterns, infrastructure cost, reliability expectations, data availability, downstream consumption, and model complexity. Question 9. What metrics would you monitor for a production ML model? I monitor 3 layers: infrastructure, data, and model behavior. Infrastructure metrics include latency, error rate, throughput, CPU, memory, and cost. Data metrics include schema violations, missing values, outliers, and feature distribution shifts. Model metrics include prediction distribution, confidence, drift, and when labels arrive, accuracy, precision, recall, or business-specific metrics. I also monitor downstream KPIs because a technically healthy model can still hurt the product. While answering, cover service metrics, data quality, prediction distribution, model performance, drift, business KPIs, alert thresholds, dashboards, and delayed ground truth challenges. Question 10. What is data drift, and how would you detect it? Data drift means the input distribution seen in production changes from the distribution used during training. I detect it by comparing feature distributions across time windows using statistics like PSI, KL divergence, KS tests, missing value rates, category frequencies, or embedding distance for unstructured data. Detection should be feature-aware because not every shift matters. I set thresholds carefully and connect drift alerts to performance checks. Otherwise, teams get noisy alerts they ignore. Make sure to explain feature distribution changes, concept drift distinction, statistical tests, population stability index, embedding drift, monitoring windows, thresholds, and alert fatigue. Question 11. How do you design an automated retraining strategy? I design retraining around evidence, not habit. Some models need scheduled retraining, such as weekly demand forecasting, while others should retrain when drift, performance degradation, or new labeled data crosses a threshold. The pipeline must validate data, train candidates, compare against the production model, and promote only if quality gates pass. For high-risk systems, I include human approval. Automated retraining is useful, but uncontrolled retraining can silently ship worse models. In your answer, discuss scheduled versus trigger-based retraining, label availability, drift signals, evaluation gates, human approval, rollback, resource planning, and avoiding unnecessary retraining. Question 12. How is Kubernetes used in MLOps? Kubernetes gives MLOps teams a consistent way to run containers for training, batch jobs, pipelines, and model serving. I use it for scheduling workloads, requesting CPU, memory, and GPUs, isolating teams with namespaces, managing secrets, and scaling inference services. Operators and tools like Kubeflow, Kserve, Ray, or Argo build on Kubernetes. The trade-off is complexity, so I only expose abstractions that data scientists actually need. Be sure to mention container orchestration, scalable training jobs, model serving, resource requests, GPUs, auto-scaling, namespaces, secrets, operators, and platform consistency. Question 13. What are best practices for containerizing ML applications? For ML containers, I keep images reproducible, small, and secure. I pin dependencies, use a stable base image, avoid baking secrets into the image, run as a non-root user, and add health checks. For GPU workloads, CUDA, driver, and framework compatibility must be explicit. I usually separate model artifacts from the serving image unless startup speed requires bundling them. Smaller images reduce deployment time and attack surface. While answering, cover slim images, pinned dependencies, non-root users, reproducible builds, model artifact handling, GPU compatibility, health checks, security scanning, and startup latency. Question 14. How would you orchestrate ML workflows using tools like Airflow, Kubeflow, or Prefect? I model ML workflows as DAGs with clear task boundaries. Ingest, validate, transform, train, evaluate, register, and deploy. Each task should be idempotent, parameterized, observable, and able to retry safely. Airflow is strong for scheduled data workflows. Kubeflow fits Kubernetes native ML pipelines. And Prefect is flexible for Pythonic orchestration. I avoid giant monolithic tasks because they make debugging, caching, and reruns painful. Make sure to discuss DAG design, idempotent tasks, retries, dependencies, artifact passing, scheduling, parameterization, observability, backfills, and when each tool fits. Question 15. Why is experiment tracking important, and what should be logged? Experiment tracking prevents ML development from becoming a spreadsheet and memory exercise. I log hyperparameters, metrics, loss curves, artifacts, code version, data version, environment, tags, and notes. This lets me compare runs fairly, reproduce promising models, and explain why one candidate was promoted. Tools like MLflow, Weights and Biases, Neptune, or SageMaker experiments provide this structure. Good tracking also improves collaboration between data scientists and platform engineers. In your answer, cover comparison across runs, hyperparameters, metrics, artifacts, datasets, code versions, environment details, collaboration, reproducibility, and tools like MLflow or Weights and Biases. Question 16. How do you safely deploy a new ML model version? I deploy models progressively. First, I validate the model offline and in staging using realistic inputs. Then I may run shadow traffic, where the model predicts without affecting users. If results look safe, I use a canary rollout to a small traffic percentage and monitor latency, errors, prediction distribution, and business metrics. For product decisions, A/B testing may be needed. Every deployment should have a rollback path. Be sure to mention staging validation, shadow deployment, canary rollout, A/B testing, automated rollback, monitoring, approval gates, compatibility checks, and business impact measurement. Question 17. What validation checks would you add before promoting a model to production? Before promotion, I validate both ML quality and production readiness. I check schema compatibility, missing values, feature ranges, evaluation metrics, fairness constraints, robustness on edge cases, and comparison against the current production model. I also test latency, memory usage, container security, model signature, dependency compatibility, and API integration. The candidate should beat or justify replacing the current model. Promotion should be a gated process, not a manual guess. While answering, include data schema validation, performance thresholds, fairness checks, robustness, latency, memory, explainability, security scanning, integration tests, and comparison with current production model. Question 18. How do you address security and governance in an MLOps platform? Security in MLOps covers data, code, models, and infrastructure. I enforce least privilege access, encrypt data, manage secrets properly, scan containers, and maintain audit logs. For governance, I track lineage from data to features to models to deployments, including approvals and ownership. If PII is involved, masking, retention policies, and access reviews matter. Models are production assets, so they need the same discipline as software services. Make sure to cover access control, secrets management, audit logs, data privacy, model lineage, approval workflows, vulnerability scanning, PII handling, compliance, and least privilege. Question 19. How would you scale model training for large datasets or deep learning workloads? I first identify the bottleneck: CPU preprocessing, data loading, GPU utilization, memory, or network. For scaling, data parallel training is common, while model parallelism helps when the model is too large for one device. I use efficient data formats, caching, distributed storage, checkpointing, and orchestration through Kubernetes, Ray, Spark, or managed cloud training. Scaling is not just adding GPUs. Poor input pipelines can leave expensive hardware idle. In your answer, discuss distributed training, data parallelism, model parallelism, GPUs, checkpointing, data loading bottlenecks, spot instances, orchestration, and monitoring resource utilization. Question 20. What is training serving skew, and how can you prevent it? Training serving skew happens when the features or transformations used during training differ from those used at inference. It can come from duplicated pre-processing code, stale features, time leakage, missing values, or inconsistent encodings. I prevent it by reusing transformation logic, using a feature store, validating schemas, testing sample requests end-to-end, and tracking feature distributions in production. Even a strong model can fail if its inputs change silently. Be sure to explain mismatch between training and inference transformations, feature stores, shared code, schema checks, point-in-time joins, integration testing, and monitoring production features. Question 21. How would you implement rollback for a bad model deployment? Rollback requires planning before the incident. I keep immutable model artifacts, version serving containers, deployment manifests, and registry stages. If monitoring detects bad latency, errors, or harmful predictions, I route traffic back to the last known good model using deployment controls or a feature flag. I also verify feature compatibility because older models may expect different inputs. After rollback, I preserve logs and predictions for root cause analysis. While answering, cover model registry stages, immutable artifacts, deployment versioning, traffic routing, configuration rollback, data compatibility, monitoring triggers, and incident communication. Question 22. How does infrastructure as code help MLOps teams? Infrastructure as code makes ML platforms reproducible and reviewable. Instead of manually creating buckets, clusters, IAM roles, databases, and endpoints, I define them in Terraform, Pulumi, CloudFormation, or similar tools. This improves environment parity across dev, staging, and production, and supports disaster recovery. Changes go through code review, testing, and audit trails. For MLOps, that consistency is critical because hidden infrastructure differences can break pipelines. Make sure to mention reproducible environments, Terraform or Pulumi, version control, reviewability, environment parity, disaster recovery, compliance, automated provisioning, and reducing manual cloud changes. Question 23. What changes when applying MLOps practices to LLM or generative AI systems? LLM systems still need MLOps basics, but new artifacts appear: prompts, retrieval indexes, embeddings, guardrails, evaluation sets, and provider configurations. Evaluation is harder because outputs are open-ended, so I combine automated metrics, human review, golden datasets, and safety checks. Monitoring should include latency, cost, hallucination signals, refusal rates, and user feedback. If using external APIs, I also track provider version changes and fallback strategies. In your answer, cover prompt versioning, evaluation complexity, retrieval pipelines, embeddings, hallucination monitoring, guardrails, cost tracking, latency, feedback loops, and model provider dependencies. Question 24. How would you optimize cost in an MLOps platform? I optimize cost by measuring first. I tag resources by team and project, track training jobs, inference endpoints, storage, and GPU utilization. Then I right-size instances, use autoscaling, schedule batch workloads, use spot instances where safe, and apply storage lifecycle policies. For inference, model compression, batching, caching, and scale to zero can help. The key is balancing cost with reliability. The cheapest platform is not useful if it misses SLAs. Be sure to discuss compute right-sizing, autoscaling, spot instances, batch scheduling, storage lifecycle policies, GPU utilization, caching, model compression, observability, and cost attribution by team or project. Question 25. A production model suddenly shows degraded business metrics, but service health looks normal. How would you debug it? I would treat it as an ML incident, not just an application issue. First, I check recent model, data, feature, and infrastructure changes. Then, I inspect prediction distributions, feature freshness, schema violations, drift alerts, upstream pipeline failures, and segment-level metrics. If labels are delayed, I use proxy metrics and shadow analysis. If impact is significant, I roll back to the last known good model. Afterward, I document root cause and add missing monitors. While answering, walk through incident triage, recent deployments, data quality, feature drift, label delays, upstream changes, prediction analysis, rollback criteria, stakeholder communication, and post-mortem actions. If you are still with us, congratulations. You are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.